definition of the derivative function. Definition of the derivative function. It's only one. And here it is. F prime of x equals the limit. We wrote it, but I want to emphasize and make sure we understand this, of the difference quotient for any function. For any function, if we are asked to find the derivative using the definition of the derivative function, this is the only definition we have. In the next chapter, I'm sure you're going to be happy. We're not going to do this. We're going to use differentiation rules, which obviously are much easier to work with than this. So please choose a function so we can determine its derivative. 21 through 31. Let's choose anything you would like to look at. I think we should look at least two of those. Maybe a rational, maybe a radical, and a polynomial, whatever you want. But I would suggest two.
26.
Okay, so we want to look at 26, which is this, and 30. They are pretty similar. This is t to negative 1/2, and this is x to 3/2. So they will be very similar. These two, 26 and 30, will be very similar. I would recommend 27, and I would recommend 28 or 29. But since this caught your eye, I would like to do 26. So let's look at 26, and then 27, and then 29. Is that or 28, whatever. Is this okay? 26, 27, 29? Okay. There is nothing new. Obviously, you'll see. There is nothing new. We're going to do the same thing over and over. So we said 26. And this is g of t equals 1 over the square root of t. And yes, immediately I'm going to change it into this. Just in case. We'll see. The problem is asking us to find, to determine its derivative using the definition. Well, the only difference is that right now I cannot use x, I would have to use t. So then g prime of t equals the limit as age approaches 0 from g of t plus h minus g of t divided by h. I had to substitute f and g for f for g and x for t. Okay, so now limit as age approaches 0. I will keep this for now because this doesn't allow me to do anything here, so I will prefer that for now. 1 over the square root of t plus h minus 1 over the square root of t. We've seen this before when we calculated limits. So that's why we discussed initially the difference quotient, then we discussed the limit operator and how to deal with it, and now finally we put these two together, the limit with the difference quotient. So again, do not forget about the limit operator. So again, you're going to give me what for the top? You're going to give me we are subtracting fractions. So you're going to say the square root of t times the square root of t plus h. Agreed? Good. Then you're going to give me the appropriate adjustments for the top. The square root of t, and this one, the other one, the square root of t plus h. Very good. So then that's what we have because it's 1, 1. So the square root of t minus the square root of t plus h. This is h over 1. I will flip it and put it in front. So I'll flip 1 over h into h over 1 into 1 over h. So the new expression for the function is this. H, the square root of t, the square root of t plus h, and the numerator is the square root of t minus the square root of t plus h. I should have said from the very beginning, I rushed, I'm so sorry, we have to plug in 0. G of g of t minus g of t. 0 over 0, of course, is 0 over 0. It's an indeterminate case, and we have to simplify as much as possible. And now what are we going to do? Let me just caution you that this is the problem. This is no problem, and this is no problem. This approaches the square root of t, and this approaches the square root of t. So these are fine. This is the problem. But there's nothing I can do to h or the other two because they are not the problem. I cannot do anything. So what is my only chance here? Conjugate, very good. The square root of t plus the square root of t plus h. Awesome. Thank you, Ella. Excellent. Oops. Good. So now I copy the denominator, h, the square root of t, the square root of t plus h, the square root of t plus the square root of t plus h. Remind me to ban you from choosing. I'm kidding. Can anyone give us the numerator? Yeah, some of these problems are quite long. T. Yes, you either put parentheses, careful, t plus h, or you distribute. Be very careful. So we've done something similar several times this semester. So this equals to limit sh approaches 0, right? We have t minus h over h, the square root of t, the square root of t plus h, the square root of t plus the square root of t plus h. These two go away. I don't like to do this to you. We should just simply write it one more time. These two pieces will go away, right? So let's write it one more time. So negative h at the top, and h the square root of t, the square root of t plus h, the square root of t plus the square root of t plus h. And finally we simplify. Remember, we have 1 at the top. And now this will be final. This is the last step, and only now we drop the limit operator. Please make sure that it did not disappear from the very beginning all the way till the last step. Please do not drop the limit operator. So that equals, the numerator is -1. Can anyone give us the denominator? Of course, when h approaches 0, this is the square root of t. Where does this go?
Square root of t.
Very good, the square root of t. Where does this go?
2.
Plus, exactly, multiply by 2, the square root of t. So finally we get -1 over 2. This is t, the square root of t. This was changed into t. A lot of work. Questions? One more time. The function was 1 over the square root of t. What does this represent one more time? The function that gives the rate of change of the original function at any point where this function is the differentiable. So this is the function that gives the rate of change of this function at any point t where this function has a derivative. Questions? Okay. So the next one we decided to be 27. I think this is g of x, the square root of 9 minus x. So the same definition. Please write the definition so you get used to it. Limit as h approaches 0 from g of x plus h minus g of x divided by h, and then fill it in. Please tell me what to write. We've done this before. This is a much simpler situation. 9 minus x minus h, careful, and then minus the square root of 9 minus x divided by h. Same idea, the same thing has to be done. When I plug in 0, I get 0 over 0. So what do I continue with? I multiply top and bottom by, yes, 9 minus x minus h plus the square root of 9 minus x, square root of 9 minus x minus h plus the square root of 9 minus x. Do not drop the limit operator. I will write the denominator. And please give me the numerator. Nine minus x minus h, remember we had to distribute. And then minus, it's safer to write minus first and then in parentheses and distribute later and not to forget. So the 9's will go away and the x's will go away, right? As expected, we know that. So the numerator is just negative h. All terms without h must go away, as we know from a long time ago. So the square root of 9 minus x minus h plus the square root of 9 minus x. As expected, the second thing that has to happen, that h in the denominator has to go away. And now we can drop the limit operator. So what is the final form of the derivative of this function? So this goes to 0. Nothing else changes. The square root of 9 minus x plus the square root of 9 minus x is 2 the square root of 9 minus x. Questions on this, please? Questions? What does this function represent? It's the derivative of this function, right? So it gives the slope of the tangent line to the graph of this function at any point where this function is differentiable. Can you give me an example of an x value at which this function will not be differentiable? Just one value.
8, 10.
So the domain of this function is 9 minus x greater than or equal to 0, which means x less than or equal to 9, negative infinity 9. But I'm saying I want one point at which this function is not differentiable, but you cannot go outside of the domain. When the function doesn't exist, you cannot say that at 10 the function is not differentiable. We're talking about its domain. I'm talking about the domain of the function. Give me one point at which this function is not differentiable. There's only one point. Exactly, 9. Because the square root of 9 minus x is in the denominator here, and it's not in the denominator here. The function is defined at 9, but its derivative does not exist at 9. Therefore, this function is not differentiable at 9. It has a vertical tangent. Very good. So you understand we're not talking about the function being not differentiable when it's not defined. If it doesn't exist, of course it cannot be differentiable. Very good. Any questions here? Any questions? Okay, so now I want to go back and write the title that I said, please wait. I didn't want to divulge anything. So 2.8 is the derivative function. The derivative function. So we're going to go back to that 2.7, and we'll come back to it. Okay. One last time this chapter, I'm going to torture you with this. Well, this time, P has coordinates A, and the y coordinate is, but if this is A, then this is, very good. Okay. And this is Q, but this time Q has coordinate X, and very good. Like before, we're going to draw the secant line. Like before, I'm going to ask you what is the slope of the secant line PQ. And you're going to say, yes. Very good. Over. Very good. Now, I would like you to tell me in front of f of x minus f of a over x minus a, I will have limit of what? Yes. X minus a approaches. Excellent. X minus a approaches 0. Perfect. Instead, we say x approaches a. Because now I still do the same thing. I'm still bringing Q closer and closer to P, but this time x approaches a. What do you think this will equal to? So before you answer, one more time. Every time we determine g prime of x, the result is a function. G prime of x is a function. But now, I would like you to tell me what to write in front. Since x approaches a, which could be 5 or 10 or 3, the answer will be a number, comma, not a function. So this will be only f prime of, exactly. We do have two definitions for the function, for the derivative at a point. So this is the definition of the derivative function evaluated at a, or x equals a. It's a number. Now, the obvious question would be, wait a minute. I don't care for this. I don't care for this. Because I can always determine g prime. I get this. And then you'll tell me that you want me to evaluate it at 0, and I'll plug in 0. What's the point here? Why do I care about this definition? I can always find f prime of x, and then I'll plug your a in it, and I'm done. True. It's possible. Absolutely. So, however, we do have two definitions for f prime of a, but only one for f prime of x. I will ask you to find f prime of a, but feel free to find f prime of x, and at the end plug in a. That's fine too. It's the same definition. Sometimes this definition will be, however, easier to apply than the f prime of x. And if you're only asked to find f prime of 2, I wouldn't go to the extent of finding f prime of x with a definition and plug in 2 in it. It's up to you. So here's one more definition for the same thing. Okay, as I said last time, this is for the same definition. Here's the same graph, the same f of x, the same p with a f of a, but this time, of course, this is q, and of course it's a plus h. And this is f of a plus h. So can anyone give us another f prime of a? As limit, h approaches 0, very good. From what? A plus h minus f of a divided by h. So we do have two definitions for f prime of a. One with x and a, and the other one with a plus h and a. Same thing. Okay, let's practice this. And I want to talk a little bit about the notation of derivatives. Okay, on page 151. So please feel free. So this is f prime of a, and we have these problems. I would like to choose one to practice that. Finding f prime of a using the definition. Again, no one will force you to use f prime of a ever, but I like to practice a little bit with f prime of a with x minus a. It doesn't matter which one you look at.
20.
Want to look at 20? It's 27 to 32.
I said 20.
I'm sorry?
29.
29. Okay, very good. Okay, so for 29, on page 151, we have f of t equals 2t plus 1 over t plus 3. And we're asked to find f prime of a. Yes, we can find f prime of t with the only definition we have. And then at the end, just plug in a, and we're done. But I recommend let's practice the other definition, not the one with h, but the one with x, because we have not seen any example with that. So, for this function, f prime of a will be limit as t approaches a from f of t minus f of a over t minus a. So, what do we write? What do you think? I have to copy f of t. I have to copy the limit operator. So 2t plus 1 over t plus 3. T minus a in the denominator, and 2a plus 1 over a plus 3. Okay, now when you plug in a, what do you get? You don't even have to plug in here. It's f of a minus f of a over a minus a. So obviously it's 0 over 0. Good. So now you will tell me to find and by the way, which factor has to go away?
T minus A.
Of course. T minus a is the problem. If somehow I remove t minus a from the top and t minus a from the bottom, we're in business. Well done. Thank you. Good. So I have to find what? T plus 3, A plus 3. Adjustments, A plus 3, T plus 3. Now what? Carefully multiply A by 2T. You know what's going to happen. I'm going to run out of room. You know that. So A times 1 plus 6T plus 3 minus. Maybe not. There are only 4 more terms. Okay, minus 2AT minus 6A minus T minus 3. Oh, okay. Just one time I did not run out. What has to happen now? We're looking at the difference quotient. 2 things have to happen. What is the first thing that has to happen? Otherwise, I know I have an error somewhere. All terms without So, okay, let's see. Right? The 2AT and a negative 2AT and a positive 3 and a negative 3.
Correct.
And now we combine the 6T with negative T, and we combine the positive A with negative 6A. So terms without A and T have to go away. So limit T approaches A. So 6T minus T will be 5T, and minus 6A plus A will be minus 5A. Do you see where? So then this is over 1, so I'm going to flip. So T plus A, I'm sorry, T plus 3, A plus 3, and T minus A. We already see what has to happen, right? The T minus A will go away. This is what I expect. And we knew that from the beginning, right? So limit as T approaches A, 5 T minus A over T plus 3, T minus A, I'm sorry, A plus 3. Okay, finally, the problem goes away. At this point, I can drop the limit operator. So what is the limit? Remember, it has to be a number because A is a number, and it has to depend on A. There is no more T in there. So the numerator goes to 5. This goes to A plus 3. This is just A plus 3. So it's going to be A plus 3, everything squared. So now if I say A is 1, you're going to say fine. It's 5 over 9. 5 over 16, I'm sorry. If I say A is 0, then I have 5 over 9. If I say A is 2, then I have 5 over 25, and it's 1/5. So for any A, I can determine the exact slope of the tangent line to the graph of this function f of t. The exact slope, or the instantaneous rate of change at that point. Yes, Felix, you had a question? Go ahead. Okay. Questions from you here, please. Questions? Okay, I would like to look at a word problem. This caught my eye, number 42. So let's read number 42. 151, yes, at the bottom. A roast turkey is taken from an oven when its temperature has reached 185 degrees Fahrenheit. and is placed on a table in a room where the temperature is 75 degrees. The graph shows how the temperature of the turkey decreases and eventually approaches room temperature. By measuring the slope of the tangent, estimate the rate of change of the temperature after an hour. Ready? We need this. Ah, wonderful. Okay, I'm looking for a pencil because I don't want to use a marker on the block. Okay. So the rate of change after an hour, 60 minutes. So I see already they drew the tangent line. I'm going to try to estimate rise over run. So obviously the slope of the tangent line here will be negative. The temperature decreases. So what about the rise? Hard to come up with, right? So I'm going to say roughly, so this is 0, 50, 100, 150 to 100. So I'm going to say if this is 150, I'm not sure. If this is 50, I'm going to say 90. So between 150 and 90. So this is 60. And now I also have to estimate the run. You would say what here? So this is 15, 20. And here, are you going to say 110? Okay, so 90. Okay, so rise 60, run 90, but negative. So the rate of change for problem 42, 151. So the slope of the tangent line at P, negative, and we said 60, rise over 1, and we found it to be 90, correct?
Right.
So this is negative 2/3. Not good enough. Why? It doesn't have a measurement unit. Please remember, I cannot give full credit if you have a word problem and y is measured in miles and t is measured in hours, and you just write negative 2/3. Okay, so what is the measurement unit here? It's the measurement unit of the y-axis over the measurement unit of the x-axis, right? So remember the rate of change when I drive home and you call me and you say, are you driving? Yes, I'm driving. And you're asking me what is your speed? I'm not going to say I'm driving at 50 miles. I'm going to say I'm driving at 50 miles per hour, right? So please remember the rate of change is always, will always have a measurement unit that comes from the top and a measurement unit that comes from the denominator. So what is the measurement unit here? Is degrees per
minute.
Minute. It was minute, yeah. So degrees Fahrenheit per minute. So please remember the measurement unit. Questions for me here? I would like to look at another problem. Like, for example, something like this. So let's read a couple, and you'll tell me what catches your eye. If an equation of the tangent line to the curve at the point where A2 is this, find f of 2 and find f prime of 2. That's one possibility. If the tangent line 2 passes through the point, find f of 4 and f prime of 4. So I would like you to choose a problem like this. Okay, so let's look at 20. if the tangent line to y equals x, tangent to y equals f of x at 4, 3 passes through 0, 2, which is the point, comma, find two things, f of 4 and find f prime of 4. So this is our question. This is what they are asking us to determine. Find f of 4 and find f prime of 4. Okay, let's take a look at a graph. The point 4, 3 is this. The point 0, 2 is this one. Now I read. The tangent to the graph, I don't know where the graph is and I don't care. So the tangent to the graph of the function at 4.3 passes through this point. So the function can be here, the function can be here, I don't really care. Maybe we should just have an idea or just graph, doesn't matter, but let's say it's this function. Maybe it's easier to see. So the tangent to the graph of f of x at 4, 3, this is the 4, 3, passes through this point. Find f of 4. What do you think? F of 4. We're not looking at f prime of 4 just yet. We want to determine f of 4. It's not a tricky question. Exactly. Of course. Of course, that's where the tangent is, right? Right, f of 4 is 3. This is the point. That's why for a second I said, oh, maybe we don't need to graph the function, but yeah, because it's very clear. Good. So now you're correct. So f prime of 4, how do I determine that? I have 2 points. So f prime of 4 is y2 minus y1 over x2 minus x1. So this point is 4, 3, and this point is 0, 2. I have 2 points. I can determine the slope of the tangent line. So 3 minus 2 over 4 minus 0. The top is 1, the bottom is... In this case, there is absolutely no measurement unit because everything is abstract and we don't have any connection to real life situations. I want to go back to 2.8 for a minute and talk about notations. Very important. F prime of x or dy over dx mean the same thing. Two different notations. And again, you will ask, why do I need to even think of in terms of dy over dx? You will see how important this notation is a little bit later in chapter 3 and chapter 4. So they mean the same thing. This is called the Leibniz notation. You don't have to memorize that. I'm not going to test you on that, but it's the Leibniz notation and they are the same. Now, what do you think this means? Obviously, this is the derivative. We call it the first derivative. This is the second derivative. How will the Leibniz notation look like? d2y over dx2, indeed. Same notation, same thing, but two different notations. Yes?
You were very specific when you wrote this one, but I
way is that we write d squared y and then dx.
Very good. Awesome. So when we find the second derivative, we differentiate the first derivative. Is that clear? So when I have the function and I differentiate the function, I get f prime. If I want to determine the second derivative, then I have to continue differentiating the derivative. Good. So now dy over dx, which can be rewritten as d over dx of f of x, same thing, slightly different notation. When I want to find the second derivative, it's d over dx of, apply to this, apply to d over dx of f of x. And it changes into d2y over dx2. So the derivative with respect to x of the derivative with respect to x. You can also write y here. So d over dx of dy over dx is the second derivative of y with respect to x the second time. The second derivative of y with respect to x the second time. Is it somewhat better? So, of course, the third derivative, and so on and so forth, would be d3y dx the third time. Now, we don't have differentiation rules. I'm not going to ask you to find the second derivative using the definition of the derivative. Absolutely not. That's not what I would like to do. But I would like to look at one more example, and we can stop. I know we have 7 minutes left. I would like us to look at the graph. And please choose any graph from here. I'm going to copy it to the best of my abilities. And I would like us to graph the derivative. It's a perfect example of the relationship between the function and its derivative.
What page is that?
That is on page 162. And I'm looking at problems 4 through 11. Trace or copy the graph of the given function. Then use the method of example. I don't know what that says, but it doesn't matter, to sketch the graph of f prime below it. Below it.
Number 9.
We want to look at number 9. Perfect. So I'm going to copy that graph. Please, I'm not gonna write it here because as you see, I write big. So because we need two different things, one below the other, please. So this will be the function, and identical, perfect copy right underneath. So notice that the y-axis are in the same vertical. So I'm going to copy the function. And in number 9, so this is number 9 on 162. I don't know those numbers, but it doesn't matter. So this is the graph. I don't know what I mean is I don't know how high this is. I don't know what the x-axis. I can't tell. It doesn't matter, though. Okay, ready? Okay, so first I'm looking at this piece of the function, and I see the slope is negative. I'm not sure. I'm just going to come up with some numbers. I'm going to say that this is 4, and I'm going to say that this is 3. So then everywhere the slope is between negative infinity and this point, whatever that is a negative rise of a run, which is negative 3/4. So negative 3/4, I can make it slightly easier. Let's say it's 4/4. Okay, so I'll say it's negative 1. So the derivative of this function, since this is a line, and I measured the slope to be 4/4, rise over 1, but it's a negative slope. So the derivative, so this will be f prime of x. All the graph here will be f prime of x. This graph is f of x. So for this piece, between negative infinity and this number, I don't know, let's say negative 2, the function, the derivative is negative 1. What happens at this point? Careful. It's not differentiable. If it's not differentiable, the derivative will not be continuous there. Okay. So now I'm going to say that this is 1 and 1, or 2 and 2, it doesn't matter. Still the slope is 1. So this is the situation. At this point, the derivative does not exist because there is a corner in the function. The function is not differentiable at 0. Okay. Now, again, I measure this. They appear to be parallel, but let's say they're not. I don't know. But I still have to write 2/2 again, right? Because it's the same, it appears to be symmetric. So this is negative, and negative, by chance, it happened to be negative 1 again, okay? The function cannot be differentiable at 0 and at this point because it has a corner. Now, this, since it's symmetric, I'm going to say 4 and 4 again. So here it is. This is the graph of the derivative function for the function you pick, number 9. Corner, the derivative is discontinuous. Corner, the derivative is discontinuous. Corner, the derivative is discontinuous. Why? Because the function is not differentiable at those points. It does not have a unique tangent. It has a negative tangent and a positive tangent. It has a negative tangent and a positive tangent. Positive tangent and negative, positive and negative. See, here the tangent is negative, which is this number. Here the tangent is positive, which is this number. And on the other side is 1.